Hello grade 12s and welcome to this exam practice video on momentum and impulse. In this question we're going to be making use of the principle of conservation of linear momentum, and we will also be drawing vector diagrams. This question says the 17.5 gram bullet in the diagram below moves with a speed of 55.60 meters per second. It strikes an 8.45 kilogram block resting on the table, and then the bullet bounces straight back with a speed of 12.60 meters per second. Now, before we move on to the questions, how about we start off by choosing a direction as positive? Let's choose forwards, or the original direction of the bullet, to be the positive direction, and that means that when it bounces back, its speed is going to be in the negative direction. We're dealing with two objects. We're going to call the bullet object 1, and we have its mass. We have its initial velocity, which we are taking as positive. We have its final velocity, which is backwards, which means that we're taking this as negative. And then we have object 2, which is the block. We have the mass of this block, and we know that since it is resting on the table, its initial velocity is going to be 0 meters per second. Now, fortunately, we've been provided with the diagram, and we can see the bullet is approaching the block, the 8.45 kilogram block. We see from this diagram that the block is then going to move a distance of 1.32 meters forward or to the right, as indicated over here. Now we can go on to the questions. Question 4.1 says, state the principle of conservation of linear momentum in words. I'm not going to write this principle down, but it states that the total linear momentum in an isolated system remains constant. For writing this down, you're going to obtain 2 marks. It's very important that you learn it off by heart so that you don't leave out any key words. Question 4.2 now says, calculate the magnitude of the velocity of the block immediately after the collision. So in order to perform this calculation, we can make use of the principle of conservation of linear momentum. Often, when you're asked to state a principle, it implies that you're going to be using it later on in the question. Not all the time, but it is a good hint about what you may be required to use. So for question 4.2.1, since we're dealing with a collision, we're going to be making use of this principle of conservation of linear momentum. Remember that this principle deals with 2 objects. So we say the sum of the initial momentum of object 1 and object 2 is going to be equal to the sum of the final momentum of object 1 and object 2. So we can now plug into this formula the values that we know. The mass of the bullet is 0.0175 kilograms. Its initial velocity is positive 55.60. We add to this the initial momentum of object 2. Its mass is 8.45, and since this object is at rest in the beginning, we know that its initial velocity is going to equal to 0. Please remember, momentum is a vector, and therefore when you substitute the velocities into this formula, you need to provide them with the correct directions, or your answers are not going to be correct. After the collision, the mass of the first object is still 0.0175. This is the bullet. At the end of the collision, it moves backwards at a speed of 12.60. So we're going to plug into the formula negative 12.60. Then we have the mass of the block, which is 8.45, and we do not know its final speed. So we're going to leave this as V final of object 2. We can now manipulate this formula and plug values into our calculators to find that the final velocity of object 2 is going to be equal to 0.1412 meters per second. We are only required to find the magnitude, and therefore we do not need to indicate direction. But just to make it clear to the marker that we have chosen object 2 to be the block, and they have asked about the velocity of the block immediately after the collision, let's go further and say therefore the final velocity of the block is equal to 0.14 meters per second, and we can round this off to 2 decimal places. You're going to obtain 1 mark for your formula, 1 mark for your substitutions, and 1 mark for your final answer, which does not require a direction only because you were asked for magnitude. Question 4.2 says that we need to calculate the magnitude of the frictional force between the block and the table if the block moves 1.32 meters before stopping. So stopping implies that its final velocity is going to be equal to 0. There are 2 things or 2 events taking place here. Firstly, there is a collision between the bullet and the block. After this collision, the block continues to move forward and the bullet moves backwards. We are looking at what happens after the collision. So this motion of the block along the table. Okay, so the collision is over. Now, very important, or something that will help us or guide us here, is that the frictional force is not a force that exists as a result of the collision. And we therefore will not be making use of the impulse momentum theorem or Newton's second law in terms of momentum, because that law is normally used when we are dealing with a collision. It can be used in this case, but here we are not dealing with a collision. So instead, we're going to go back to our basic principles. We know that the net force is equal to mass multiplied by acceleration. This is Newton's second law that you learned in grade 11. We are looking for the net force. When this block moves along the table, there is only one force acting on it, and that is the frictional force. So the F net is the frictional force. We have the mass of the block, and although we don't have acceleration at this point, we do know the initial velocity of the block or initial speed of the block. Remember, the speed or the velocity at which the block leaves the collision is the initial speed for this motion along the table from this point over here to that point over there. So we have the initial, this is going to become the initial speed. We have the final velocity, initial velocity and final velocity. We also know the distance that this block is going to travel. So how about we make use of an equation of motion in order to determine the block's acceleration as it moves along the table? We choose one formula from the equations of motion that will work. I'm going to go with v final squared is equal to v initial squared plus 2 acceleration change in x. We know the final velocity is 0 because it comes to a stop. At the start of its motion along the table, its initial velocity is 0.14. This is towards the right, so we keep it as positive. And then we say plus 2 acceleration, which we don't know. The distance was given to us as 1.32 meters. We manipulate this formula, and in the end we find out that the acceleration of the block is equal to negative 7.55 times 10 to the power of negative 3 meters per second squared. This is the acceleration of the block, which makes sense since it is negative, implying that the block is slowing down. We don't need to interpret this negative because we are not yet at the final answer. We are looking for the net force, which is the friction force. The net force is equal to mass times acceleration. Therefore, grade 12, the frictional force is equal to mass times acceleration. This, once again, is only because the only force acting on the block is the frictional force, and therefore this is the net force. We know that the object's mass is equal to 8.45. The acceleration we plug in with its negative as negative 7.55 times 10 to the negative 3. When we plug this into our calculators, we find out that the frictional force is negative 0.06 newtons. Now this answer is negative, which actually implies that the net force is 0.06 newtons backwards. But remember, the question only asked for the magnitude. So it said, calculate only the magnitude of the frictional force. So we therefore say, therefore the magnitude of the frictional force is equal to 0,06 newtons. And this is the final answer to this question. This question is out of 5 marks, so you will probably obtain your marks as follows. 1 mark for your equation of motion, 1 mark for your substitution. 1 mark for F net equals MA, 1 mark for substituting, and 1 mark for your final answer, giving you a total of 5 marks. Now we can move on to the last question, which says, draw vector diagrams, not to scale, to illustrate the relationship among or between the initial momentum, the final momentum, and the change in momentum for the bullet. Now, a moment ago we were dealing with the block. We now need to think again about the bullet. This bullet starts off moving towards the right, which means that its initial momentum is in the positive direction, and we don't need to calculate it. We just need to remember that it is positive. After the collision, however, the bullet moves backwards, meaning that its final momentum is going to be in the negative direction. We remember that when we draw the vector diagrams, we use the formula that P initial plus the change in momentum is going to give us the resultant, which is P final. So I'm going to draw a very rough sketch over here on your page, right? We know that the initial momentum is going to be towards the right, okay? And we're going to label this P initial. When we draw the final momentum, we draw it from the tail of the first vector to the head of the last vector. The tail of the first vector is over here. So that means that the final momentum will be drawn in this direction. Remember that we add the change in momentum to the initial momentum in order to get the final momentum. So the change in momentum will be added to the initial momentum. So we go to the head of the initial momentum, and we add the tail of the change in momentum. Here's our change in momentum. And this over here is a vector diagram representing the relationship between the initial final momentum and the change in momentum of the bullet. Again, what we have done is we have taken the initial momentum, we have added to it the change in momentum, and then the final momentum is the resultant, which we attach from the tail of the first vector to the head of the last vector. Over here, you're going to get 1 mark for each of your vectors. It's important that you label them, although you don't need to indicate the actual magnitude of the momenta. You're welcome to go and calculate them, but it was not necessary because your diagram does not need to be to scale. So grade 12, this brings us to the end of this video. This question was out of 13 marks, by the way. We will be going through another exam practice video, so I hope that you will join me in that video. Thank you so much for joining me here.